Hello everyone, and welcome to today's webinar on data science covering basic statistics through digital mill hub. It's Alamgir Hossain, Deputy Coordinator, Monitoring Innovation Learning (TIB) and founder of Digital Mill Hub Bangladesh. This learning platform is totally my personal initiative as volunteer task, and it's never responsible of TIB as my present organization. It's my great pleasure that all the emerging M&E professionals of national and international level have joined today. Now, Honorable M&E professional, it's especially a great moment to have Dr. Rahmatullah Imon is a speaker today. He was my direct mentor whenever I studied at Russian University Department of Statistics. I honored and grateful to him that he gives his valuable extra effort for us from his very busy schedule. Dr. Imon is a professor of mathematical science, Ball State University, USA. He has more than 32 years of working experience in data science, statistics, mathematics, and research article as full professor position and visiting professor or scientist in different countries' university. He took an early retirement from his Ball State University, USA job in December 2023. Currently, he is serving as the director of the Center for Interdisciplinary Research and the director of Career Center at Voluntary University, Rajshahi. Dr. Imon's areas of specialization is regression diagnostic, robust regression, and outlier detection, multiple analysis, sample reuse methods, time series analysis, statistical computing, and graphics, and environmental statistics. Dr. Imon has published several books and over 150 research articles in referred journal and proceeding of international conference. However, we will learn from him today about population, sample, data, census, sampling technique, different chart, descriptive analysis, or inferential statistics analysis. Before leaving, I request again all of you, please remain unmute you during session and you will get open discussion or feedback at the end of the session for 20 to 30 minutes. So keep question or suggestion at your mind. The recorded webinar session and presentation will be circulated through WhatsApp group as well as your registered mail. I am requesting to Dr. Imon sir to start today's session. Over to you.
Thank you, Mr. Alamgir Hossain, and I welcome you all to this particular session on basic statistics in data science. So basically, it's a webinar concerned with data science, but I am, my area of research is statistics, so I will try to explain how statistics can contribute in data science at this modern stage. So now this is all we know that statistics deals with data. And this is our present time data, which is really, really unthinkable, say 20 or 30 years back. So now we are in the era of big data, and big data is not only in terms of volume, it's also in terms of its velocity, its variety, variability, veracity, and value. And now everything is under data. When you talk over telephone, when you watch any movie, when you are using any kind of internet, every Facebook, everything, all kind of social media, we have data over there. So data is not only like asking people, hey, what's your height or what's your weight, that what we had in 100 or 120 years back. This is no longer, we're no longer in that kind of, world. So data is diverse now. Data is different. Data is, unmanageable sometimes. So we are now in the era of big data. So that's why everything has changed. Our theory, our practice, the way of collecting data, analyzing data, everything is different now. And that's why statistics also had a different role in this particular modern time. So you see that when I was a PhD student, we usually use this kind of floppy disks for storing our data, but perhaps now you can find them in only museum because nobody is using them anymore. Our data has been really, really big, and it's growing very fast in every year. So we are having different kind of units of storage, and our capacity has been growing up. And now, where is our role as statistics people? So this is data science, and it's a kind of more interdisciplinary kind of research. We have almost everything. All we know that data science basically came from business. It's the daily transaction of Walmart, which ultimately contributed to the big data kind of stuff. So it came from business. Uh, Statistics people, they used to develop software and all kind of stuff so that they can analyze it. And then we have computer scientists. They were involved in storing and managing data. We have machine learning approach, which is a kind of blend of computer science and mathematics and statistics together. Software development research, so everything is coming up. So statistics is now a part of the whole game. So we are not claiming that we are the only people who are contributing to data science. There are many other stakeholders, but we have a big share in there, and our contribution is not negligible in any way. We have a very big area of contribution in data science. Now, what is the role of statisticians in data science? Because nowadays, data science is more inclined to computer science. So computer scientists are now taking lead in this data science research. And there is a reason, because the way we're having our data, so data generation, collection, storage, management, all these kind of things are now being done by the computer scientists. So now one may ask that where is our role as a statistics people in this game? Well, now the question is that as long it's true that computer scientists, they have a very significant role in data storage, in data management. But when the analysis of data is concerned, because why we collect data, we have to analyze them, right? So our ultimate objective is to get some information, get some knowledge by analyzing data. So when the analyzing of data is concerned, then of course that should be done by statistics people, because anyone can analyze data, and if they do it without considering its merits and demerits, they can put lots of nonsense as well. Because if you don't know what you are doing, if you don't know what's the most appropriate way of dealing with this particular type of data, you can produce lots of nonsense than sense. So that's why there is a dark side of indiscriminate analysis of data, and only a professional statistics people can tell you how to use the most appropriate way of analyzing data. So as long as the data analysis is concerned, we'll always get an upper hand. So definitely we have something to play in this particular kind of research. Now, let's begin with, so I will mostly talk about the statistics part today as a part of data science. Now, if we look back to the first formal definition of statistics, that's in 1911. Whitney Ewell, he wrote the first ever book of statistics, and the title of the book was An Introduction to the Theory of Statistics, and it was published by Charles Griffin in 1911. And in that particular book, he gave a formal definition of statistics, and he said statistics is the statistics is the science of analyzing data, is the science of collecting, describing, and analyzing data. And still, many of us believe in this kind of definition, but that has been changed because now we have a huge, change in our data collecting process and describing and analyzing. But still, we talk about data in statistics. So statistics mostly deal with data. Now, the question may immediately come at this point that if data is the essence of statistics, then why we don't call it data science at the very first place? We could say data science because this is a subject which deals with data. But at the same time, statistics mostly concerned at the time of its development, it was mostly concerned with information regarding state. So the word statistics came from Italian word statista, which is definitely about state. So we used to get information regarding state and analyze them. So that's why the word statistics came. It's not, of course, we use data, but data was a part of the game. Our main focus was to know about a state, and data was a tool at that time. So that's why we use the word statistics. But at the time when statistics came into existence, we had this kind of concepts, and mostly we had a in the initial stages, all kind of statistical analysis was concerned with census. That means we used to get information from the entire population. Okay, but at some point we understood that it's not that easy to get information from every individual of a population. So that's why we started collecting sample and start getting information from sample statistics. So that's why we had a population in the initial stage, and we were trying to get some kind of characteristic of the population, which we say variable. Data are the kind of counts, measurements, whatever you say, which to know about the population. And the census, as I told you before, that was about the entire population. And any kind of characteristic that comes from population, we call it a parameter. And when a parameter is estimated by sample, we usually call it statistic or sample statistic, which comes from. So the difference between a parameter and a statistic is that we do the same kind of thing, but parameter is related with population, and the statistic is related to sample. So now we can just show you the quick difference between population and sample stuff. Population is the whole group, and sample is the part of the group. In population, this is the group that we want to know about, but in sample, we definitely know, because once we collect sample, we know about those information. Population characteristics are called parameters. Characteristics are called statistics in sample. In population, parameters are generally unknown. So basically, we try to know about some unknown things, because the population is so huge that we may not know about the entire thing. So we can only guess, or we can have some idea. So usually parameters are unknown. But once you get information, once you get data, you can just do some kind of manipulation on them. And now what you get by statistics, those are known. Say, for example, we don't know the population mean, but we know the sample mean, right? So that's easy. Now, usually parameters are fixed because parameter is the representative value of the entire population, but statistics vary with sample, because if you just go and ask 100 people, you will get some information. If you go and ask another 100 people, you will get definitely something different. So those may be very close, but those are not necessarily the same. Only by chance you can get two exactly same information from two different samples, but that's highly unlikely. Whenever you change a sample, you'll get a different kind of sample statistics. But that's not a problem, because that's the beauty, that's the variability that always comes into play. So these are the kind of basic differences between sample and population. And we have basically two types of data. One is called qualitative data, which is mostly the categorical kind of data, which is, say, for example, if we want to level someone, say, for example, your ID, your bank account, your credit card, those numbers that you see over there are just to identify you or distinguish you from other people. So that's the kind of identification mark. So those number doesn't really mean anything. So these are basically qualitative data. When you try to express some feeling, which is a qualitative data. But when we can count our stuff, when we can measure things, those are the quantitative data. Usually we use description and levels in qualitative data, and in quantitative data we use counts and measurement. Now, when we go to quantitative data, we have two types of quantitative data. One is discrete, which is countable, Say, for example, number of your siblings, number of students, you can count those. But we can also have some kind of information like, the total amount of blood in your body, or your, weight, your height. These kind of things are basically continuous. So you can measure them, but you cannot really count it, just like number of boys or girls. We cannot really do that. So that's why we have two different types of quantitative data. One is discrete, which is countable, and the continuous, which is measurable. Now, we have different kind of levels for qualitative and quantitative. So I can just give you, these are the name nominal, which is just a kind of ID, which doesn't really mean anything. In ordinal, we have an order. I will give you an example. Interval level and ratio level. So let me quickly go to an example. So these are 4 steps that what I have just mentioned. Nominal, basically, it's kind of names. Ordinal, where there is an order. Say, for example, when you talk about level of education, we can say primary, high school, college, university, PhD. So we have a level of education. And of course, one is superior than other, right? So there is an order between these two. Say, for example, you can say that, when you give a score to your, instructor in a class, so you can say 1 is poor, and then 2 is, medium, 3 is acceptable, 4 is good, 5 is excellent. So there is an order in 1, 2, 3, 4, 5, right? So these are some numbers that what we give in qualitative data. In interval, in quantitative, we have 2 types of thing. Interval, which is more related with some kind of data like temperature, IQs, and ratio is a general kind of data which can be used in every kind of quantitative data, like when you measure anything, your height, your weight, your income, expenditure, amount of time you sleep, etc. So I'll just give you a very quick example, and that will distinguish you between data and numbers. Say, for example, when it comes to a number, 10 is always bigger than 5, right? Which is always true. 10 is always bigger than 5, but which is not necessarily true in a data, because 10 inch is not more than 5 miles, right? So when we talk about data, usually data is, it's considering it's a measure unit of measurement. We don't usually say that I earn 10 what? $10, 10 British pound, So we have to say something after 10, right? The unit of measurement. And when you put unit of measurement after number, it may not be same as before. Say, for example, if I say 10 kilogram, which is definitely not more than 5 tons, right? So it's not always the case. Now, all we know that in terms of number, 10 equals 5 times 2. If you multiply 5 2 times, it's 10. But that's not true if someone is having an ID 5 and someone is having an ID 10. Can we say that number 10, who is having an ID number 10 is twice more intelligent than the guy who is holding ID number 5? No, it's just an identification. It's a nominal kind of stuff, right? But it doesn't really mean any kind of thing that 10 is 2 times bigger than 5. Now, in terms of number, 0 means absence. Say, for example, you have $100, you have $100, and you spend $100. How much you have now in your pocket? It's 0, right? You had something, you just use that, and after that, you don't have anything. So 0 means absence, but which is not true in data. When I say 0 degree temperature, 0 degree centigrade, does it mean that there is no temperature right now? Of course, it's a cold weather, right? Or even 0 degree Fahrenheit. Does it mean that there is no temperature at all? Of course, it's a temperature, right? So 0 in terms of spending money and 0 in terms of a temperature is not the same. In a similar way, when you, say, for example, the price of a commodity is $150, right? I'm sorry, $140. You don't have in your pocket that amount of money. You have $40 and you have 2 more friends. who are having $50 and $60. And if you add your money together, which is 150, so now you can buy that product. Three of you can buy it jointly because your total amount of money is now 150, and which is definitely more than 140. So if the price is $140, three of you can purchase it because you have more money than the price of it. But is it true that, say, you are now trying to solve a puzzle and three guys are having their IQs 40, 50, and 60? So if you add your IQs together, can it be more than 140, the IQ of a genius, which is not the case? So the way you can add money, you cannot add your IQs in that way because IQs are not the general kind of thing. So the difference between 0 and, which is temperature indeed, and IQs, these are called scale. So those are not the ratio. In ratio, you can do all kind of mathematical operation. You can add, you can subtract, you can multiply, you can divide. But when it comes to scale, those look like numbers. Definitely 150 is more than 140, but you cannot add, subtract, multiply, and divide those things in a regular fashion. So that's the difference, why we have different types of levels of measurement and etc. Now let us talk about some graphical tools that Mr. Alamgir asked me to talk about. So can everyone hear me?
Yes, sure.
And can you see my slides as well? I just want to double check.
Yes.
Okay, thank you so much. Now, let us talk about some graphical displays of data, and let us begin with this qualitative data. Say, for example, in an election, three candidates are running, and they got this amount of votes, 7 votes, 5 votes, and 10 votes, and we can always use the tally mark to count the votes, and after that, we can present it.
এত কষ্ট করে এসে কি করবেন কোন সকালে চলে
ওকে
কি করে লাবণী খাওয়া নিয়ে ব্যস্ত এখন ওকে
I'm sorry. Now I see that I was muted. Okay. So when you count your votes, and after that, you can just present it in a kind of frequency table. So now A got 7 votes, B got 5, and C got 5. Now we can just present it in a pie chart. So the name of pie is coming from the American pie. You know that a pie is a kind of dessert that we have in US. So we can just present things in that way. And usually we create angles. So whenever we have the counts, we can use this simple formula, frequency times 360 degree divided by n. And that gives you angles for A, B, C. And you can just give a sharing in a circle. And that will tell you that A is having 7 votes, B is having 5 votes, and C is having 10. So you can just, so the biggest angle is the dark one, which is the vote of C. The blue one is the vote of A, and the tan one is the vote of for B. So we can just present it in a chart, which we call pie chart. Now, donut is very similar to pie chart. So if you just take the middle portion off, so now you see that it looks like a donut. So in the previous pie chart, we had 3 people. One is having 50%, other was having 30, and the third one is having 20. So we can see exactly the same picture here, but this is no longer a pie. It looks like a donut because we have taken the middle portion off, right? So this is just a kind of pie chart, but slightly different, and we call it a donut chart, which is another dessert indeed. We can use bar graphs, and which is exclusively done for a qualitative data. So if you have a qualitative data, you can use bar diagram or bar graph. Please remember, in bar graph, there must be a space between 2 bars. Those should not be connected with one another. So since these are discrete, there should be a gap between bars. And this is also, the second one is also another example of bar graph. But you see that the second one is like a column as well, right? So sometimes we call it a column graph. Of course, column graph is a kind of bar graph, but since it looks like columns, we can call the second one a column graph. Pareto chart, the difference between Pareto chart and other kind of bar charts is this, that in a Pareto chart, we have an ordering. So usually we put the biggest one on top, and the second biggest, second, third biggest, third, and so on and so forth. So you see here that the biggest one was A, and which is of course 200, but the second is D, no, not B, right? So we put D because it had the highest frequency, 181, and the third highest was C, 176, and the fourth highest was B, 157, and the lowest one is 143. So we just have an order here, and so it's a bar graph, but it maintained the order. We can also have a side-by-side chart. So say, for example, when we have same question asking to two different groups of people, like male, female, we ask them that why you are late in class, and these are the answers that males and females are saying. So you can just put them side by side to see that what's the difference between them or how they're different. Say, for example, the late excuse, that one may be overslept, one may be traffic, etc. And this is the way how the male and female are, saying. And of course, if you look at the clothes, then it's a less excuse from a man, but it's a more excuse for a female because they usually take more time to dress up, right? So that's a common kind of situation. So we can just side-by-side graph can tell you the difference in opinions between 2 or 3 or several groups of people, which is sometimes very useful. For quantitative data, we can use a histogram, which is very popular, which is basically like a bar diagram you see here. It's just like a bar diagram, but the difference is, since these are for continuous data, there should not be any gap between the bars. In a bar diagram, there must be a gap between bars, but here there shouldn't be any gap between bars. Those should be attached with one another. So that's the only difference between a bar graph and a histogram, right? Frequency polygon, sometimes we use the midpoints of an interval and we connect them so that we can have a frequency polygon. So just like here, we have price of 3D TVs. So we have several classes. We are considering their midpoints and we're just connecting them through a polygon, and that's a frequency polygon. Sometimes we use stem and leaf plot, which is exactly same as the histogram. Now you can see the difference between these two. So in a stem and leaf plot, say, for example, when you look at the histogram, you can only see the height. You don't see the information anymore once you construct a histogram. But in a stem and leaf plot, you can see the height. At the same time, you can see the number. Say, for example, here the highest frequency is against number 7. If you look at the stems, we have 4, 5, 6, 7, 8, 9. So highest frequency is for 7, but we at the same time, we know what are the numbers corresponding to them. We have 72, 73, 73, 75, 75, 78. So if it was a histogram, we could only say that we had 7 observations there, but we couldn't tell which are the values of every individual. So the advantage of a stem and leaf plot is this, that it not only is telling that which group has the highest frequency, but at the same time, it can tell you that which are the real values of those observations. Line graph, which is also a kind of graph that can be used for both discrete and continuous. So say, for example, for discrete data, you can talk about the number of students in a class, number of tickets sold in a day, number of product reviews, number of employees in a company, and you can just get it over year or time, whatever. For continuous data, you can look at the age, blood pressure, weight, temperature, and speed, and you can just put it in a kind of graph like this. Say, for example, this is the average monthly rainfall for 2 different cities. So once you have those information for each month, you can just correct them through lines, and that will give you line graphs, and it can tell you about the pattern or trend of the data, right? That you see that we have more rainfall. This is most basically a Western kind of example. So we have more rain in January and December than June and July. It's opposite in the tropical countries. Say, for example, in Bangladesh, it's totally opposite. We have most of rainfall in June, July, August, and very less rainfall in December and January, right? So sometimes data are also, they are related with the, tropical area, season, reason, etc. So this is a winter kind of data, and if it is a summer data, like countries from tropical countries, it would be definitely a different kind of data. Now I talk about some sampling techniques, because sampling is very important in statistics as well. We always prefer some random sample. Why? Because if you personally choose some people for getting information, there could be a personal bias. You can always go for your like-minded people. You can always go with your relatives, your family, your friends, and they may not represent the population. So we need to collect samples in a purely random way. And the easiest way of doing that is a simple random sample. So it's just through a lottery. So you put the name of the populations in a piece of paper or whatever in a kind of a lottery ticket, and then you can just use something like a bingo, and you can just randomly draw some numbers, and you just pick those people who are being selected as member of your sample, and everyone has an equal chance of being selected here, and this is called a simple random sample. Now the problem is that if you have some definite different part of population, say for example you have male and female in a class, and you would like to have form a committee of say 5 with your students. Now if you randomly select the students, this 5 could be all male, right? Or it could be all female. So although you definitely want to have male and female representation in your committee, if you do it in a random way, there is no guarantee of that, because you are just selecting people by chance. So you never know who will be selected, right? But what you can do, you can say for example, if I see that 60% of my students are male and 40% of them are female, then you can just tell that, or you may want that out of 5, I should select 3 male and 2 female, because these are the proper representation of my class. So what you can do now, you can divide your population into 2 groups, male and female, and then you can randomly select 3 male from males and 2 female from females, right? And if you do that, we call it stratified sample. So what we're doing, strata is a kind of part of population that you are subgroup of population. You're dividing your population into several subgroups. Within that group, everyone is homogeneous. It's all male or it's now all female. And then you are randomly, so once you do this stratification, after that you are employing the simple random sampling technique, and that gives you a kind of sample that we call stratified sample. So here we see that since we have 3 blue balls, 6 red balls, and 3 green balls, when I'm going to pick 4 samples out of these 12, I'm going to pick 2 red balls, and those are number 2 and 8 randomly, and I'm going to pick only 1 green ball, which is 10, and one green ball, which is number 5, and 1 blue ball, which is number 10. So we are doing it randomly, but we are doing the stratification first, and after that we are randomly selecting some. We have another sample which is very popular in terms of our real life study. So instead of an individual, we can now sample cluster. We can choose streets. We can choose localities. We can choose some particular regions, right? So instead of individual, I am collecting, say, for example, like districts, region, etc. And every member of that particular area are my sample. Say, for example, instead of selecting, say, 20 or 30 people, what I'm doing here, I have 5 clusters, 5 different subgroups here, and I am randomly picking 2 clusters out of 5. So originally I have 5 clusters in my population, and I'm randomly picking 2 out of 5. And 1 is the first one and once we get that selected cluster, I'm just going and asking all people of that particular, belonging to that particular cluster, and those will be the member of my sample. So this is the way how we can do the cluster sampling, and which is sometimes very useful because it's very difficult to go to door by door and doing a random sample when you do it in a large area. Perhaps it's much easier that if you just divide a large area into different kind of segments, different kind of regions, and then you pick that kind of regions, it will be much more easier for you to get sample. Systematic sample, which where you take samples in every alternative. Say, for example, you can just go like this, that I would like to pick, pick a sample in every three. So I would just, from 1 to 3, I'll randomly pick 1. If the selected one is 2, then it will be 5, just 3 with that. So it's 5, 8, and 11. If the first sample is 1, then it should be 4, 7, and 10. If the first sample is 3, then it should be 3, 6, 9, and 12 if there is 12. So this is the way how we go and pick samples. Convenience sample, sometimes it's very useful because doing a random sample is really, really difficult, especially if the population is huge. So it's really difficult to maintain the sampling design. But on the other side of the story, we can just use internet nowadays. We can just send email to our friends. We can ask questions through Facebook and get some kind of answer. Of course, these are very fast and very useful, but at the same time, it may show some kind of bias because if you want to do a survey through your email, only people who are connected with you will receive that email, right? So there is no guarantee that it will be representation of the entire population. The same thing is true with Facebook. Only your Facebook friends will be, allowed to get into this survey. So these are very fast, convenient, but at the same time, not necessarily the proper representation of the data. And here is an example. So say I'm just going to collect people who are close to me, and that's convenient for me because I can just grab them quickly, but it may not be the proper representation of the true population. So that's the disadvantage of convenient sample. The advantage part is that it's very easy, less time consuming, and very fast, and sometimes very less expensive as well. Okay, so here we try to give some differences between the 2 key branches of statistics. One is called descriptive statistics. That what we usually, once we get our data, we analyze it, and we get some information from the data. And whatever we get from data analysis at the first place, data summary, etc., those are called descriptive statistics. But that's not the ultimate objective of our study. Why we do a study? Say, for example, we want to know the characteristic of students of a university, right? For our ease, we are asking, like, we're selecting 100 students because it may be very difficult for me to go and ask all, say, 50,000 students of the university. So for my convenience, I'm going and asking like 100 or 200 or 300 students. And I get a descriptive statistics from there. But that's not my objective. My objective is to talk about the entire population. So my sample may be of 300 people, but I would like to comment on the entire population, right? So say, for example, if I get some average GPA of 100 university students, but once I comment, I say that this is the GPA of this university, right? Say, for example, how many hours a particular group of people sleep. So Russia, my hometown, is called as the most happiest city in the world because we sleep more than any other part of the world. Now, how do you know that? So have you asked every Russian people that how many hours you sleep? No, you have perhaps asked 3 or 5 or 100 1,000 people, and you get a figure, and which is definitely more than another kind of study, and you have noticed that it's significantly different than other city, then you are claiming that Russia people are sleeping more. So you are getting your descriptive statistics based on, say, a sample, but ultimately you are making a comment on the entire population. And that is the inferential, right? And here is an example. A random sample of 45 university students show that 16 of them are left-handed. So you are asking 45 students, and this is descriptive, but at the same time, you are saying a poll consisting of 345 residents was conducted to know the average house rent in Dhaka. So your objective was to know about the average house rent in Dhaka, about entire Dhaka. You asked 345 residents, and they say it's 17,338 Dhaka. So this is a statistics. Of course, this is a descriptive statistics, but we are using that to talk about the entire Dhaka people. And if we do that, it's inferential. So that's the difference between these two. In qualitative data, the kind of descriptive statistics that we use is a proportion, which is a kind of ratio. So say number of left-handed students or proportion of left-handed students, proportion of MEL, proportion of people living in campus or out off campus. So these are the kind of proportion that we can always use for qualitative data, which is a very popular kind of descriptive statistics. For quantitative data, we can use this kind of stuff. We can use the arithmetic mean as a measure of center. We can use a geometric mean. I'm not really going to define all this. All of you know about those. I just mentioning the names. Harmonic mean, which is another way of computing the average. We can use median, which is the mid value. We can use the mid range, which is the average of the two extreme observations of the data, largest and the smallest, and take the average of them. We can use the mode, which is basically a qualitative data, and which is the most frequent observation that occurs in the data set. So we can use that. We can use weighted mean. Sometimes, say for example, you are looking for scores of a student, and so you can get different types of activities to a student. You can give him homework, you can give him a final exam, you can give him assignments, and you may not give equal weights to all of them, right? So usually we give more weights to our exams than our homeworks and assignments. So you can put different types of weights. So when you are computing the CGPA, you are not blindly doing the average of their homeworks, their assignments, their presentations, their final exams in a similar order. So usually give different kind of weightages. And if we do that, we call that kind of average as a weighted average. Trimmed mean, sometimes when you have some unusually extreme observations in the data set, you may ignore some of your extreme observations to compute your average. And if we trim this kind of observation, we can compute the trimmed means in this way. Winsorized mean is a kind of trimmed means where you can replace your extreme observations by the largest of the good observations that you believe in. So this is a kind of trimming, but in trimming you are just ignoring the whole observations. In winsorizing, you are replacing your extreme observations by the next available good observations that you think. Now, this is not the point. My point is, once you have a data, you have to decide that what kind of mean you have to use here. Say, for example, I have 5 different data sets. The first one is the score of 20 batsmen. I'm sorry, yeah, in 20 innings, score of a batsman. So you are looking for the average, run or average score of a batsman when you have 20 innings. We have growth of bacteria. In the third one, we have quarterly cells. And in the fourth data, we have copper content in wheat flour. So these are 4 data sets. Now the question is the same. We have same common question. What is the central value of this data? What's the average of this data? Now the question is which average you have to use here, because I'm not asking you, or nobody is telling you that whether you have to use a median or a mode or arithmetic mean or geometric mean. These are data. How you use your average. Nobody is telling you which average you have to use here. You have to decide, because you may be the only statistics guy in your organization. So there is nobody to tell you what to do. So you have to now decide, right? Now, what should be the most appropriate kind of measure of center? Well, now here we go. We say plot the data. And why this is so, I'll just give you explanation very, very quickly. Plot the data. If the data is a perfect scatter, just like this, score of 20 innings of a batsman, then the most appropriate measurement is the arithmetic mean as an average. Let's see what happens. We see here that the average score is 40. And if you look at the data, you will see that 40 is just going through the middle of the data. We have almost same number of observations above and below the average, right? So it's a kind of center value. There is no question on that. So 40 is the average arithmetic mean, and which makes sense because 40 is also the central value of the data, which is going through the middle of the data set. Now look at this. When you plot it, it's a growth of bacteria. You can see an exponential growth here, right? And if you just do the arithmetic mean, which is 204, what's happening now? We have only 3 observations above the mean, the geometric mean, and we have almost like 7 or 8 observations below. 3, 6, 7. 7 below and 3 above the arithmetic mean, which is 204. So is 204, the arithmetic mean, is a representative center for the data. It's not in the middle of the data, right? Now look at the geometric mean, which is 47.37. How many observations are above the geometric mean? 5. How many below the geometric mean? 5. So now you see 47 is the central value for this particular data. So when you have an exponential growth, you should use a geometric mean. You should not use an arithmetic mean, right? Okay. Now here is the quarterly cells, and you can see a different pattern. You can see some kind of seasonality or periodicity here, right? What happens if you try to find the center? If we usually don't look at anything. We just go and compute it by average, right? And what's wrong? Well, if you just compute an arithmetic mean, out of 12, you see only 4 observations are above the arithmetic mean, 38, and 12 are below, right? But if you go for the harmonic mean, because there is a harmonicity here, there is a periodicity here, so the most appropriate mean should be harmonic mean. And if you do that, you see that 8 observations are above the harmonic mean and 8 observations are below the harmonic. So harmonic mean is the center of this data. So all our data, and if we don't look at the graph, we don't see that what kind of graph should be used, what kind of measure should be used here. So one may blindly apply arithmetic mean for all these 4 different data sets, right? And he will be in a trap, because arithmetic mean is not necessarily the most appropriate measures of center for all this data. It may be good for the first one, but definitely not for the second and third. And look at the final one. The copper content, we have a big outlier here. Arithmetic mean is 43. Only 1 observation is above the mean and 9 below. So 43 cannot be a representative value for this center. But if you use median, or if you use trimmed mean, we have like half above, half below. So that is more representative value for this one. So we cannot notice all these kind of things unless we grab the data. That's what I really told you, that if you I was muted. I don't know why, but I think now I am back. Can you hear me now?
Yes, sir. Yes, sir. Carry on.
Okay. Thank you. So now what I'm trying to say that, if anyone asks you to compute the measure of center, you grab the data first, and from graph, graph will now guide you or tell you that what kind of measure you have to use here, because you have plenty of choices, and graph can guide you to go for the appropriate one. Okay, so now I'm just saying that this is the kind of thing that you can always do. For qualitative data, we can use mode. For quantitative, we should graph first. If it's a perfect scatter, just as I said, we have to use arithmetic mean. If there is a proportional growth, we can use geometric mean. If there is a periodicity or a harmonicity or rate of change, we can use a harmonic mean. If there is unduly extreme observations, we can use median or trim mean or winsorized mean. So these are my suggestions for measuring center. Now we can go for the measure of relative positions, because sometimes we also want to look at the positions. Say once you are giving an exam, you would like to be in top, say 1% or top 3% or top 5%, right? So those are percentiles. We can look for 1/4 of the data, and that's our quartiles. And for overall description of data, 5 numbers are very, very important, and we call them the 5-number summary. And these 5 numbers are the minimum, the first quartile, the median, third quartile, and maximum. And I can tell you that there is a famous plot. Because of my time shortage, I cannot give you all kind of plots, but I'm sure that all of you are familiar with box plot. Box plot is nothing but this 5-number summary. So they just display this 5-number summary. So in a box plot, there is a box in the middle, and the box contains median in the middle, and it's the lower end point is the first quartile, upper end point is the third quartile, and there are 2 lines which go from box to the extremes, and that's minimum and maximum. So basically, the box plot is a graphical representation of these 5 numbers. So this is the 5-number summary. Is a very it can give you a very quick kind of information about a data set. Now for measures of dispersion, the variability, because sometimes it's very important for us to look at the variability, because even if the average is the same, the variability may not be the same as well. Say, for example, the average of 50 and 50 is 50. The average of 0 and 100 is also 50. But these are not the same thing, right? So you also need to look at the variability sometimes, and that's why we have to look at those. And these are some, I'm not really wasting your time because all of you know about it. I'm just, giving you a quick short list. We can have a look at the range, which is the difference between the maximum and the minimum observation. We can look at the standard deviation, how the observations are deviated from the center, which is basically the arithmetic mean or the average, the mean absolute deviation. So instead of a square deviation, you can look at the absolute deviation. You can look at the median absolute deviation, because in a mean absolute deviation, you are looking at the deviation from the mean, but you can look at the deviation from the median as well. The interquartile range is another way of measuring dispersion, which is the difference between third and first quartile. So these are the kind of measures of dispersion that you can always use. And sometimes we would like to, for comparison, we can look at some relative measure of dispersion. One of them is coefficient of variation. Another could be standard score. Now, why we like those kind of things? Because once you compute your standard deviation, or if you compute your average, it always gives you the measurement, the unit of measurement. But when you divide them in this way, you can get rid of the unit of measurement. So now you can get a definite number. So you can compare one number with another number. As I told you before, that you cannot compare 5 miles with 5 years or 5 inches, but you can compare 3 with 5. So CV, the coefficient of variation, is an unit-free measure. So you can compare things very, very easily. Like same thing is true with the standard scores or a z-score. While you subtract the mean and divide by the standard deviation, and after that you get an unit-free kind of measurement. So you can compare them quite easily. Otherwise, you cannot really, you are comparing apple with oranges, which is not a good kind of thing. Now, we can also look for the different ways of, cases here, like our inferential, when we come to our inferential statistics, basically we do two types of things. One is known as the estimation of parameters, and the other one is called test of hypothesis here. Now, in estimation of parameters, we also have two types of estimation. One is called point estimation. So what you are trying to do, you are trying to estimate your population stuff by a single number. And that's why we call it a point, because you are just using one single number for the entire population. So it's a point, and that's why we call it a point estimation. And we have some properties here for point estimation. One is known as unbiased estimator. Unbiased means that if you keep estimating your stuff by sample information, and if you do it for many, many times, on average, you will see that your sample statistics is converging to the true value of the parameter. Say, for example, if your population parameter is theta, and if you use X bar as your statistic, then expected value of X bar should be equal to theta. That means if you take the expected value of a statistic, and if that is equal to the true value of the population parameter, then we call it unbiased. It's converging. And now you see that here we have two different estimators. One is the blue one, which is not converging to the true value theta, so which is biased, but the other one, which is an unbiased. The other one is known as efficiency. Efficiency means how it's varying. So lower variance is always welcome, because if your variability is high, it's difficult for, say, for example, you have a batsman who is scoring 0 today and 100 next day. So you do not know what he would do next time, right? But if you see someone is scoring 40 today and 60 next day, when he's going for the third innings, probably you will guess that he would do something in between 40, 60, or like 30 or 70, whatever. But if it's 0 and 100, you have no idea that what you would do next time. So we always look for less variability for the quality of our prediction, right? So that's why less variance is welcome, and a kind of a statistic which has less variability, we call it more efficient. And sometimes we call it best estimator. Best means, in statistics, best means lowest variance. So that's the kind of terminology that we have. Consistency, it tells you that if you increase your sample size, and if we see that the pattern of statistics is getting more close to the true value, then it's consistent. Say, for example, here we see that when n equals 25, the variation is the highest. But when you have 50 observations, the variation gets less. And when you have 100 observations, the variance is even smaller. So that means the variance is getting reduced with the increase in sample size. If that is the trend, we call it consistent. If you increase your sample, you'll get closer to the true value of the parameter. So these are some good property of estimators that we would like to want. And we can just use different kind of statistics to estimate the population parameters. Say, for example, if I am interested to estimate the population mean, I can always use a sample mean for that. If we want to estimate population standard deviation, we can use a sample standard deviation for that purpose. If we want to estimate a population proportion, we can use a sample proportion for that. So these are very, very simple and commonly used kind of stuff. And at the same time, instead of a point estimate, because if you just want to use a single point, then there is always a risk of missing the target, because your value may not be exactly hitting your a particular point. And that's why when you are in a shooting competition, you not only you have just a particular point, you have a board in front of you with different kind of level of circles, right? Of course, your target is to hitting at the middle, but you can sometimes maybe a little off targeted, and you can just hit somewhere close to the real point, right? So interval is a kind of estimation like this, that of course point estimate is more precise, but it's at the same time it's very difficult to achieve. So it will give you a more flexibility that you can just if you can estimate things within this interval, then I'll accept that it's a good kind of estimate. And that's the difference between a point estimate, which is just one shot, and interval estimate is giving you a little flexibility that you can do it several times and you can be in this particular interval. If that is the case, you are fine. I'll accept that it's a good kind of estimate of that we're having. And in this situation, what we have a point estimate, of course, in the middle, but at the same time, we have a margin of error. So we allow a little variation, and we add and subtract that margin of error with the point estimate, and that gives you a kind of interval. And if any statistic falls within this interval, I'll accept that as a good estimate. And if an estimate goes beyond that interval, I'll say that this estimate is no longer a good one. And how we can compute, and these are the kind of basic things that we have here. Level of confidence, that we have to have a probability statement here, that once you look for an interval, what is the coverage of your interval? So how many times your sample information is within that particular interval? If the coverage is good, higher, that means your chance is higher and the quality of estimation is good. If it's the probability is small, the level of confidence is small, that means you may be off target, so the quality of your estimation may not be good. Sample size, of course, because sample size is a factor, it can always help you to get the interval, and standard error, which means the variability. We always want less variability here as well. So the confidence interval, usually alpha is a probability of a confidence interval, will not include in the population parameter. So when I say alpha, which is a small quantity, which is the probability of missing the target. So 1 minus alpha is the probability of hitting the target. So 1 minus alpha should be in the interval, and alpha should be outside of the interval. So it's a kind of notation, alpha. It could be any other notation, but usually alpha tells you that what is your level of confusion, level of not including the estimate in the interval. That's alpha. Okay. Now we are talking about estimating a population mean, mu, and all we know that once we try to estimate mean mu, we use X bar, right? So what we do now, we add and subtract the margin of error with X bar. You see here that how we constructed this interval, X bar minus something, X bar plus something. And what are those two margin of error? If you look at this margin of error, we have Z. Z is a standard normal distribution, right? And sigma over n is the standard error of X bar. So basically the margin of error contains two things. One is the value of the distribution, and the other one is the standard deviation of the statistic that you are considering. Sigma over square root of n is the standard deviation of X bar, and Z is the distribution of this. So if, and that's what I'm now saying, that if X is a normal distribution with mean mu and variance sigma, I'm sorry, standard deviation sigma or variance sigma square, then if you compute a statistic in this form, X bar minus mu divided by sigma over square root of n, this distribution is a standard normal. The standard normal distribution means that it's a normal distribution having mean 0 and standard deviation 1 or variance 1. Okay, now the next question is that if the population variance is unknown, if sigma is unknown, then how you can compute X bar minus mu over sigma over square root of n, because your sigma is unknown. Now, if sigma is unknown, what you can do, as I told you before, that if the standard deviation is unknown, the population 1, you can use the sample standard deviation, right? So you can replace sigma by S. But the problem is that when you do that, this distribution is no longer a normal distribution. If sigma is there, it's normal. But if sigma is not there, you replace sigma by S, the distribution is not normal. And what was that distribution? So that someone whose name was William Gossett, in 1908, he found that distribution, and he used the pen name student to derive it because he used to work in the Guinness company, and Guinness did not allow him to use his name because he used Guinness data in his paper. So he had to use a different name, a pen name, and his name was a student. So when the paper was published in a famous journal, Biometrica, in 1908, it was under the name student, and that's why the distribution of this guy is this particular distribution is known as student's T distribution. So what's the difference between T and standard normal? In standard normal, we know the value of sigma. In student's T, we don't know the value of sigma, and we estimate that with S, and we have a different distribution now. Okay, so here is that how he derived it. I'm not really going to talk much about that. Now we see the difference. Now, when n is small, you see that here the black one is the normal and red one is student T. So when the sample is small, you can distinguish between these two distributions. You see that the red one has a relatively fatter tail than the black one, right? Thicker tail. But when the sample is large means only 30, you can hardly distinguish T with normal, right? Both of them are look very, very identical. And that's why in statistics, we often say that 30 is a magic number. If the sample size is 30 or more, you can use normal instead of T. That most of our practitioners know, right? Why is so? Why this is the case? The reason is here, that when the sample size is 30 or more, you can hardly distinguish between normal and student's T. So even if you use the normal instead of T, you are not really doing anything wrong, right? So that's the logic of using normal instead of T when sample is 30 or more. So that's what you see here. And in this situation, what you can do, you can also construct a confidence interval with the margin of error X bar in the middle, add and subtract, and instead of T, Z, you are now using T because the resulting distribution is T. In a similar way, you can use the population proportion and you can use a confidence interval based on these. You can use a population variance, and this time you have to use some quantity whose distribution is known as a chi-square distribution. And Carl Pearson, who derived it in 1900, and you can just construct a confidence interval in this way. So now you see that what's happening here, how we can find a chi-square distribution. So say you have several normal distributions, standard normal. If you square them and add them together, the resulting distribution will be a chi-square distribution. So when we do the variance, we usually do it in this way. We subtract the mean, we square it, add them together to compute a variance. So that's why when you look at the variance, most of the time the variance is following a chi-square distribution because it's ultimately giving you some kind of a square of deviations like the standard normal does, right? So that's why chi-square is more related with a variance kind of a stuff, and the resulting distribution is a chi-square. And the number of variables you add together is known as the degrees of freedom, right? So that's what we say. And this is the way how we can construct a confidence interval for a population variance. Here we see that we're using a chi-square here. And of course, S square is the sample information that we have. And this is the way how we can construct confidence interval. And when we have ratio of two variances means ratio of two chi-squares. Ratio of two chi-squares gives you another distribution that we call an F distribution. Okay, so here we go, F distribution. So say, for example, if U is a chi-square with n degrees of freedom, and V is another chi-square with m degrees of freedom, then U over n divided by V over m gives you an F distribution with n and m degrees of freedom. Now, why this is called F? This F came from Fisher, but Fisher did not derive this distribution. This distribution was derived by an American statisticist guy whose name was George Snedeker. But Snedeker gave this name F to show his respect to Sir Ronald Fisher, because Sir Ronald Fisher is known as the father of statistics. So although Snedeker, he derived this distribution, he wanted to honor Fisher and named it as F. Sometimes in the literature, we also call it Fisher's variance ratio distribution, because this is basically a ratio of two variances. So when we try to construct a confidence interval of the ratio of two variances, we use that. So this is the ratio of two variances, which is an F distribution, and we can use that in this way. And we can also use many other kind of confidence interval. We can find the population variances. We can find the difference of two means. So if the population variances are known, then we can use standard normal. If those are unknown, but sample sizes are large bits, 30 or more, as I told you before, that when it's more than 30, you can use a standard normal. So you can use a standard normal. If it's unknown, but but small, less than 30, it's a student's T, but it has to be equal. If it's unequal, unknown, then it's a really complicated kind of stuff, but you can still use Bonferroni T, which is an approximation of a student's T distribution, and still there is a way of doing it. You can also do the confidence interval for the difference of two means for dependent samples. Dependent samples mean that, say, for example, you are looking at a patient with the drug and without drug. So you are treating a patient, so you're not giving any drug to this guy. And after giving some medicine, you are re-examining the same patient. Now, we have two different samples, right? Before drug, after drug, but you are giving it to the same people. That means that although we have two different samples, but those people are the same. That means these are dependent samples, right? So you can teach, same group of students with two different teaching methods, right? This way, that way. And after that, you are evaluating their performance. So these are the same group of students, but they're having two different sample of information. One is with this teaching method A, and the other one is, say, for example, teaching method B. So when you compare these two performances, these are called dependent samples, because your sample objects are the same, but of course your experimental ways are different, your samples are different. But if you just want to look at how this teaching method is affecting the students, you may look at the difference of their average scores in an exam. So is it significantly different? Maybe slightly different. Now say with one teaching method, the average score is 78, with other one is 78.5. Of course, it's 0.5 more, but is that 0.5 just by chance, or it's really significantly different? We have to test it. We cannot just look at two numbers and just say, hey, this is bigger than that, so this is more. No, we have to find a way, and that's why we have this hypothesis testing, which is coming up next, that we have to find a way that whether this difference is significantly different or not. And we can also construct a confidence interval almost in a similar fashion or similar manner, and we can use the student's T in that way. We can look for the difference of two proportions by a standard normal as well. Now, what I have just said, hypothesis testing, which is coming up next. Okay, now in a hypothesis testing, we have something in our mind. We have something in our mind, and we will try to make some justification of that kind of thought, whether this is the case, whether this is true, whether this is not correct. So we have lots of thinking in our mind, and we have to find a formal, logical way of, giving an answer. As I just mentioned to you before, that I have two different teaching methods. One is giving you 78, and the other one is giving 78.5. We see a difference, but is that difference significantly, increasing the performance? Of course, if it is 78 and the other one is 88, even with looking at the number, you must say, hey, there is a big increase, 10 points lead. But sometimes 10 points may not be that big if you only have few students, right? If you have plenty of students, then of course sometimes 0.5 may be significantly different. So there are some ways of doing it. So basically that all these kind of things are coming under hypothesis testing. So in hypothesis testing, we have some statistical hypothesis, and that means that we have some idea regarding the population parameter. What is the value of this population parameter, right? Okay, how many credit hours university students are taking? How many hours I sleep if I take this medicine, right? How fast my pain will be relieved if I use this drug, okay? Whether male are earning more than female with the same kind of job. So these are the kind of questions that we may have in our mind, right? And if we just want to, do some kind of procedure of testing those kind of things, that will be known as hypothesis testing. Okay, now the most popular approach that we still use in statistics is the Neyman-Pearson setup. So George Neyman and Pearson, this is not Carl Pearson, his son, Egon Pearson. So these two gentlemen, they really gave the formal way of, hypothesis testing. Well, before their time, there was only one hypothesis, and that is just a hypothesis. Say, for example, whether it will rain tomorrow, that is my hypothesis, right? So I can just find a probability of raining tomorrow. And if I can do it, then I can just say, so say, for example, with this, I guess that the probability of raining tomorrow is 80%. Then I will say that probably it will rain tomorrow. And if it rains tomorrow, then my hypothesis is accepted, right? So that was the old kind of hypothesis. But in Neyman-Pearson setup, we have two hypotheses. One is the null hypothesis, and the other one is the alternative hypothesis. So the hypothesis that we test is the null. And if the null hypothesis is not accepted, what we should tell is this: it's no longer that whether it is true or false. Now we are also saying that if this is not correct, then what will happen? So we have an alternative thought. And when we have these two hypotheses together, null being tested and alternative, if it fails, what I should accept, alternative, these two hypotheses together, and this testing procedure is called Neyman-Pearson setup. Okay, so we have two hypotheses here, null and alternative. Now, we also have different types of hypotheses, and one is called simple and the other one is called composite. What is a simple hypothesis? The hypothesis which entirely, if you assume something about the population, then you know everything about it. Say, for example, I have a normal distribution. I know that the variance of this normal distribution is 4, but what I don't know is the mean of normal. Now, if I know a mean and a variance, then I know everything about a normal distribution. So here, 4, the variance part is known, but the mean, mu, that is unknown. And since it's unknown, I don't have any, because mu could be anything, right? Mu could be 5, it could be 10, it could be 100, it could be minus 50. Nobody knows. I don't know what is the exact normal distribution we have here, although the variance is 4 all the time, but the mean could vary. But if I now say mu is 5, now I know the distribution. Now I know that this is a normal which has mean 5 and variance 4. So all kind of normal having mean 5 and variance 4 should be the same. So there is no way that this is different from another normal distribution, right? So once I put mu equals 5, it's a normal. If I put mu equals 6, it's a normal. So whenever we put mu equals 5, mu equals 6, I know the normal distribution. So it's now completely known, it's completely specified. And with this information, mu equals 5, it's simple. With mu equals 6, it's simple. With mu equals 10, it's simple. With mu equals minus 5, it's simple. So whatever mean you put here, since the variance is known, we know the distribution. So these hypotheses are simple hypotheses. Okay, now, if we are here, So again, it's normal. Mu 4. Variance is 4. If mu equals 5, I know it because it's specified. But if my alternate thought is mu bigger than 5, is it specified? No, because it's only telling you it's more than 5. But what is the value? 6, 7, 100, million, billion? We don't know, right? So bigger than 5 doesn't really mean that how much is exactly the value is, right? So that's not specified. In a similar way, when I say mu equals 5, it's simple. The first one, the top one is simple. The null hypothesis is simple. But look at the alternate. Mu less than 5. Less than 5 means what? 0, minus 10, 4, 2.9, we don't. Again, if you look at the third setup, the null hypothesis is simple. The null is simple, but alternate is not, because it's telling mu not equals 5. If it is not equals 5, how much it is, we don't know, right? So now you see the difference, that how we can distinguish between simple and composite hypothesis. Now, this is another example, very similar to the previous one. But this time it's saying it's a normal with mean mu, variance sigma square. And now we are saying mu equals 5, mu equals 6. In the previous time, when it was mu equals 5, we said it's simple, right? When mu equals 6, I said it's simple. But are they simple now? Well, in terms of mean, of course, I know it's 5. But what about the variance? It's telling sigma square, right? That means we don't know. Sigma square is 1. It's not specified anymore. If it was 4, 25, 10, 100, then it was fine. But if it's sigma square, we don't know how much is that sigma square, right? So even if the hypothesis looks simple, because it looks like simple, equal, but still it's not simple because it's composite, because sigma square is still unknown. Unless someone gives a value for sigma square, you cannot get a simple hypothesis in this fashion. So we have to understand and realize this kind of stuff. Okay. Now, once we do this kind of thing, that our ultimate objective is to either accept or reject a hypothesis, right? We usually test for the null one. And if it fails, then of course we go for the alternative. But once we do that, we always have a risk, because it's just like a judge who is, in a trial. So we have two types of people. Someone is guilty and someone is not guilty, right? So a judge is, say, giving verdict to some, accused people. So what he can do, he can, punish a guilty person, and if he does that, if he or she does that, he or she is doing the right thing, because his or she is punishing the guilty person. But by chance, occasionally it may happen that he can wrongly punish someone who is not guilty, right? So that's a kind of error in judgment. In a similar way, sometimes what can happen, he can set free an innocent guy, and which is a good thing, right? You are not, criminal, so the judge is acquitting you. So that's a good thing, correct judgment. But it can also happen that sometimes he is sentencing someone free who is really a culprit, right? So that's a wrong thing. So in judgment, we have these two kind of things. So if we have, not guilty and guilty, two decisions, the reality, and two decisions, punish and acquit, we may have two right actions and we may have two wrong actions. The same thing can happen in a hypothesis testing, because we have two hypotheses now. One is null and the other one is alternate. And the reality is sometimes null is true, sometimes the alternative is true. And if the null is true and if you accept it, then you are doing the correct decision. But if the null is true and if you are rejecting that, you are committing an error. And that kind of error is called type 1 error. In a similar way, when the alternate is true, and if you are rejecting the null, that means you are rejecting null means you are accepting alternate. You are doing it correctly. So that's a correct decision. But if the alternate is true and you are accepting null, that means you are not accepting alternate when it is true. that's another type of error, which is called type 2 error. So in hypothesis testing, we have two correct decisions, and we have two types of error that the test procedure may commit, type 1 error and type 2 error, right? And we usually try to reduce both of them, but mostly type 1 error. Type 1 error is not convicting an innocent person. So in terms of trial judgment, court trial, we say that, never convict an innocent person. If you acquit a criminal, of course, that's not accepted, but that's better than convicting an innocent person, right? So in a similar way, in hypothesis testing, we have two types of errors, type 1 and type 2. But type 1 is more serious because you are convicting an innocent person. So you always try to keep this type 1 error as small as possible. And the other type 2 error that we also want to reduce, and that is all about the hypothesis. So here we go. That what we try to do, we would try to minimize the type 2 error. And if we minimize the type 2 error, we are maximizing the good action, right? And this is called as power of a test. So power of a test means that how much correctly you can, punishing a criminal with a very low kind of. That's the. So the main feature of the Newman Pearson that you have two different kind of hypothesis, simple and alternate, and the kind of test that you use here, we call it a likelihood ratio test, and we just find a distribution of the statistics that what we use, and we just create a region. In some region, if it falls in this region, we call it rejection. That means which is the extreme kind of situation that we have in a hypothesis testing situation. And there is a region which is a safe region that we call acceptance region. So that's the kind of thing. So just like this, that in a Neyman-Pearson setup, we may have these three types of test. In one case, our entire rejection region could be on the left cell, especially when the alternative hypothesis is something less than the null value, then usually the critical region goes to the left. When the alternative hypothesis is bigger than some quantity, then this is the third one, which is the rejection region is to the right. And when it's not equal, then we have in the middle. That means when we say that this is not equal something, that means it could be either on the right, bigger, or less, because if it is unequal, we don't know how much it is. It could be more or it could be less. So we split our region into two parts, and that's why we have this kind of rejection region on two tails. In the middle, it's acceptable because in the middle means it's close to the center of the data point. So that's why we accept it. But if it goes away from the center and it goes to the tail means it's very, very unusually extreme, then we just reject the null hypothesis. So this is the way how the Neyman-Pearson setup works in a hypothesis testing. And other setups, because in a Neyman-Pearson, both the null and alternate must be simple. But in reality, you cannot guarantee that. So if it is composite, then the kind of test that you can still use are uniformly most powerful test or the likelihood ratio test. So these are very popular tests that you may have. P-value is another important and interesting concept that we use in hypothesis testing. P-value is the probability of obtaining a test statistics, and it's telling you that at which level you can reject this your null hypothesis. Now, let me just give you an example first, and that will tell you that what is all about this. Now, usually p-value, if the p-value is small, then we are going to reject the null hypothesis because p-value is the probability of the null hypothesis to be correct. So if it is very small, that means we are going to reject the null hypothesis. And now we say that if the p-value is less than 0.001, that means it's very strong evidence against the null hypothesis. Very low. Very low means it's not reliable. The probability is very low. So we're going to reject the null hypothesis. If it is in between 0.001 and 0.01, we say it's a strong evidence against H naught. That means still the probability is very low, right? It's in between 0.001 and 0.01. Still, we should reject the null hypothesis because, but this is not very strong. This is strong now. And if it is in between 0.01 and 0.05, we say moderate evidence against the null hypothesis. So still, we are going to reject the null hypothesis, right? Because it's, we have moderate evidence against the null hypothesis. If it is between 0.05 to 0.1, we say weak but suggestive evidence against null hypothesis. We can still reject the null hypothesis because it's suggestive. We have only 10% chance of the null hypothesis to be, true. And if it is more than 0.1, we say little or no. Most of the time, we accept the null hypothesis if it is more than 5% or 10%. Now, the practitioners, they often ask, because in statistics, 5% is a kind of value that we always take it as a guarantee. We often say 95% confidence, 5% level of security. That means if the p-value is 0.05, 5% or less, we are going to reject the null hypothesis. If it is more than 0.05, we are going to accept the null hypothesis. What is the reason? What is the basis of this kind of 5%? Why this is 5%? Why this is not 1%? Why this is not 10%? Why this is not 20%? Why this is not 30%? Why it's 5%? Well, 5% is a kind of rule of thumb. There is no valid reason that why it should be like this. The only evidence that we have is this, that if we have a normal distribution, then if you look for the 5% area, it goes with 3 standard deviation from the mean, and the coverage of the entire population is about 95%. So you can cover 95%, and 95% is a good coverage in terms of probability. So if you can cover 95% and if 5% is outside, it's probably good. So that's a kind of, subjective kind of choice. But in harsh reality, p-value should vary, and it should vary according to the complexity of your problem. If you are doing a very controlled experiment, p-value should be very, very low because your chance of committing anything wrong should be very less. Say, for example, when you are giving medicine to someone, so you are giving, say, anesthesia to your patients, and can you now claim that, hey, I'm giving, I'm treating 100 patients, I'm giving anesthesia to 100 patients, and 5 of them can die just because of this anesthesia? Do you believe that people will come to you for any kind of surgery? No. So if it is 1 in a million, probably it's okay then, because there is always some kind of defect in any kind of medicine. But if it is 5%, then probably nobody will go and talk with you. But if it is like you are talking about share market, very, very unpredictable kind of situation, and in that case, if it is 5%, 10%, probably it's okay. But when it's very controlled, like it deals with the human life, and if you say that, hey, I have a medicine, and if I give this medicine, you will have 95% cases you will survive, and on 5 cases you will die, nobody will take it. But say, for example, you are treating a cancer patient where the chance of survival is very, very low. And even in that case, if the chance of, after taking this drug, the chance of survival is, say, 50%, that means 50% error, you can die with probably 50%. Some people will probably then try, because otherwise he or she won't survive, right? So even if the chance is 50%, he or she may take it, because otherwise there is no hope. But say, for example, you have just a minor kind of flu, influenza, or just a minor kind of cough. And I'm saying that if you take this medicine, out of 100, 5 people will die. Probably nobody will take that medicine. They will probably take warm water. They will have more vitamin. They will have more oranges, etc. They will never take that medicine, because that medicine can kill 5 out of 100 people, which is, of course, 5%, right, in terms of level of significance. But that doesn't really make any practical sense. If it's a cancer patient, you are giving a chemotherapy, the chance is 10% or 5% to survive. of course people will go and take it. So p-value should be always very, very subjective, and it should depend on the complexity of your problem. If you are in a complex problem, then of course p-value could be high. If it's very controlled experiment, of course p-value should be very low. Anyway, so that is my own thought about p-value. And now my final stuff that I'm going to address. Probably I'm. Alunga, how many time I left?
You can take 20 minutes.
20 minutes. Okay. So I have now some time because I just wanted to make a little, I think, rush. But no problem. If I can finish early, then of course we can have more time for question and answer. So there shouldn't be any problem. So now I'm going to talk about the analysis of variance kind of stuff, which is also a very important kind of topic that we have in statistics. Now, a question always comes in our thought that how we can talk about or get some information from observations, because in statistics we always deal with observations. We use observation, we use information to know some unknown things. Now, this is the essence of or the power of statistics, because in every observation, a truth is hidden there. So we can write an observation equals truth plus error. We may not know the truth. Truth is, say, for example, the population characteristic. We may not know that. But in every observation, the truth is hidden. Our approach is to minimize error, because if we can minimize error, we can maximize truth. Our ultimate objective is to approach to the truth, and that we can do by minimizing error. And this is the method that we call method of least squares that Gauss found. That his approach was to minimizing the errors so that he can maximize the truth. Now, what I have just said, that every observation contains truth plus error. Why this is so? Let us give this example. A simple example. I know, or I don't know, but this is the reality, that the height of a particular university student is 162 centimeters. That's the true value. That's the population value. But I don't know that. I don't know that because I don't have any record that tells me that the height of this entire university student is 162 centimeters. So as a statistics guy, if I don't know that, if I don't know the population parameter, what should I do? I'll go and ask the students that, hey, how tall you are? So I'll take the record, and after getting a handful size of sample, I'll take the average, and I will use that statistics or average to estimate the population parameter, right? The population mean. That's all we do. Okay, so what I'm doing now, I'm going and asking 10 students. Of course, this is a very small number of sample, just for your consumption. Let us make this small group of people, only 10 people. I'm going and ask the first guy, what's your height? And he said 165 centimeters. And can I not write 165 as 162 plus 3? I can write. The next guy, 171 centimeters. Can I not write it as 162 plus 9? The next one is 160. I can write it as 162 minus 2. 155, I can write it 162 minus 7. 162, exactly 162. By chance, this is the same height that the population people had. And it can be written as 162 plus or minus 0. 159, 162 minus 3, 163, 62 plus 1, 160, 162 minus 2, 174, 162 plus 12, and 149, 162 minus 30. So I can write each observation as the true value 162 plus minus some quantity that I call error, right? Okay, so now what happens if I take the average? In statistics, we say that if we take the square deviation from the average of the observation, that will minimize the distance. So the least square estimate of the height of this group of students should be the average, because standard statistics is telling you that if you take the squared deviation and take the sum and minimize it, that gives you the average. The square deviation from the mean is the average. So average is how much here? 161.8. Isn't it quite close to 162 centimeter? I did not know that it was 162. I just asked 10 students and I got information like 161.8. I'm quite happy perhaps with this result that my guess is now 161.8 and the real value was 162. So you see that it works. It works in a way that every observation can be written as truth plus error, and you can try to minimize error and that will maximize the truth. So your X bar 161.8 is quite close to the population mean 162. Okay, so this is an evidence that what we can see. So in a similar way, in regression or experimental design, what we can say, we can now say that every observation can be written as a model plus error. So previously I said truth, this time I'm saying model, because in a regression or experimental design, we use a model. It could be a linear model, quadratic model, whatever. We have some kind of model, right? Now, we try to estimate the model. And once we estimate the model, we can now also compute the total variation of the observations. And just like this decomposition, that observations equals model plus error, we can now say that the variance of observation can be also written as variance due to model plus variance due to error. And this will ultimately give you a kind of test that is called ANOVA, or analysis of variance. Now you see what we have here. So we have, say, for example, we have n observations. So let us quickly go back and see that one. Yeah, so in this experiment, what we had n observations, and we have p parameters to estimate. So now we have this kind of a structure. We have sum of square or variation of the model, which is on top. And the second part is the error. And if we add them together, we get the total. And the corresponding degrees of freedom. So since we have p parameters, we can have p minus 1. So that's what all of you probably know. And I'm not really going to explain why it is p minus 1. That our standard theory tells us. So this is the corresponding degrees of freedom, p minus 1 for model, n minus p for error, and n minus 1 for total. And now we can take the ratio of two squares. And we know that the ratio of two squares, if those are like variance, that is an F distribution. I told you before that F is the variance ratio, right? So once you have the ratio of two variances, because MS is the mean squared, which is kind of variance, MS error is a kind of variance. And if you take the ratio of these two guys, you'll get an F distribution. So based on this F, now you can see that whether this ratio is significantly different or not. Okay, so if it is significantly different, then of course the model is also important. And if it is not, why it is, if the ratio is significant, that means model is much more than error. And that's why it's important. If it is not significant, then model and error are almost the same. So if error is unexplained part and model is the explained part, right? If the ratio is small, what does that mean? That means model is not that big, right? Model is not really contributing. And that's why if the F ratio is small, we are going to say that the model is not useful because it's not explaining much. But if we see that the model is much more than error, then of course the F will be big. Bigger F will go with the very low value of P. Low value of P will tell you that the model is significant. So that's why if F is significant, that's a good news for the model. We say that the model is significant. But if F is not significant, the model is not. So this is what we can say about the ANOVA table. Now we can also going to talk about two very important concepts that we have in basic statistics. One is correlation, and the other one is regression. And interestingly, both of these two concepts were done by or developed by Sir Francis Galton. So you see here that we have a scatter plot, and the scatter plot sometimes gives you some kind of idea that whether we have a linear relationship between the variables, and if it's a linear relationship, whether it's positive or negative, how how strong is the linearity? Is it more like a scatter, or if it is, so there are lots of kind of questions that may come in our mind at this point. So here is a scatter plot between hourly temperature and weekly fuel consumption. And we see that there is a strong linear relationship between these two, and probably it's negative because if the temperature goes up, then fuel consumption goes low. It's basically an American example, especially in my part of the city in Muncie, Indiana. So this is my own data that based on my own home over there. So usually during winter, what happens? We have to burn more power to warm our houses. So that's why the fuel consumption is higher. So once the temperature goes up, we don't really need to use our burners, so that's why the electric bill goes down or the fuel consumption is lower. So this is basically the kind of situation we have. And correlation, we usually compute the correlation with the quantity that we say R, and the lowest value is +1 and the smallest value is -1. Different types of correlations that we have, we could have positively correlated, we could have negatively correlated. I have just given you an example of negatively correlated variable. If the relationship is perfectly strong positive, then we say perfect positive correlation and the value is +1. If it's perfect negative correlation, the value is -1. Here are some examples. Now you see that we have perfectly positive correlation. The first graph, the R is 1. The second one, we have a strong positive correlation, and the correlation is 0.8. If you look at the next one, of course, we have a linear relationship, and it looks positive, but not strong as two previous graph. And we say weak positive correlation, and here the correlation value is 0.3. And the next one is no correlation. We just see a scatter plot. There is no kind of pattern here. So we cannot say that whether there is any kind of correlation at all. And this is an example with R equals 0. We have no correlation. Now we're looking for the negative sides now. The first one is weak negative correlation. R is -0.3. The next one is, of course, negative, much stronger than before. And here the negative correlation is -0.8. And the last one is a perfect negative correlation. It's very strong. It's just a straight line, and the correlation is -1. We can just use our sample information to compute the correlation coefficient. We don't need the formula. Everyone knows that. So just a simple example. That's the data that I used from my home. So this is the correlation coefficient, -0.9484. Very close to -1, and we can say that we have a very strong negative correlation between temperature and fuel consumption here, -0.9484. And now we can also try to get a regression stuff. Regression means we try to explain one variable with another variable. So here y is called a response, and we're trying to understand or explain y by the variable x. So x will be now called explanatory variable. Sometimes we say y as a dependent and x as an independent variable. Y is explained and x is explanatory. X is regressor, y is regressed. So there are lots of ways how we can define these variables. But the point is that the value of y depends on the value of x. So alpha is the intercept and beta is the slope, and we have a linear relationship. You see that we have the equation. If you just ignore the epsilon, which is the error part, the remaining part is y equals alpha plus beta x, right? So this is a line. This is an equation of a straight line. But now you see that y is an observation. As I told you before, y is an observation. Alpha plus beta x is a line, which is a model, and plus epsilon is error. Didn't I tell you before that observation equals model plus error? So you see that exactly the same thing is happening here, right? Y is our observation. Alpha plus beta x is the model, which is a straight line, and epsilon is error. So observation equals model plus error. So regression is nothing but another kind of ANOVA structure that we can see here, right? Okay. Now what we can do now, we can just try to explain or find out the values of intercept and slope to get the equation of a straight line and see how it's going. So here is an example, and this is fertilizer use for the production of rice. So now we have two variables here. Rice production is the response, and explanatory variable is fertilizer. And it is expected that if you give more fertilizer, you'll have more rice, right? Because usually fertilizer helps increase the production of rice. So rice production depends on fertilizer. Rice is Y, fertilizer is X. Now let's see, this is the graph. And we can see a strong linear relationship, right? Of course, it's positive, linear, and looks very strong, fertilizer and rice production. Okay, so these are just simple way, and this is the least square technique that I told you before, that we try to minimize error. So you see that epsilon is the part of error that I told you before. So we're trying to minimize this part, and the resulting value will give you the best kind of estimate, so after solving this equation, we see this is the formula for intercept and slope. And how we get those? Just by minimizing the error part. We are getting this kind of values. Now we have this formula over there, and we can just get this kind of stuff. And that's what we get. Now, once we get, so this is what we get in the end. Unfortunately, probably I have missed a slide where we had the equation. But anyway, that's not very important. We know that, of course, fertilizer helps increase the production of rice. Okay, now once we fit the model, then what we can do, we can just now go for the ANOVA and see that whether this fertilizer has a significant impact on the production of rice. So now what I'm trying to do, I'm trying to compute the sum of square, the variance of total, the variance of regression, error, etc. And a simple way of doing that is known as R square in regression stuff. R square is the ratio of total over regression. So if the regression and the total part, the ratio is high, that means you are explaining more, so your model is good. And if R square is low, that means your SSR is small relative to your total, so you are not explaining properly. So R square is a kind of indication. Now, here we go. So now we see that what we had. So here is the model, that what we found. And for this particular model, what we say that the R square is 0.862. That means that it can explain 86% of the total variation, which is quite good, right? Usually, if it is more than 50%, we often say that's acceptable, but when it's 86%, indeed, it's really good. So this is the R square, and at the same time, we can put it in, and this is a kind of thumb rule. Of course, if it is 1, then it's perfect fit, right? If the R square is in between 1 and 0.95, we say excellent fit. If it's 0.9 to 0.95, very good fit. 0.8 to 0.9, good fit. 0.7 to 0.8, moderate. 0.5 to 0.7, acceptable. 0.3 to 0.5, poor fit. 0.1 to 0.3, very poor fit. 0 to 0.1, fit not acceptable. And if it is 0, it's an imperfect fit. So this is basically some rule of thumb that we usually use. There is no theoretical justification behind those, just from our lots of experience that we have with the data analysis, we get this kind of rules of thumb. And that's why ANOVA is more, reasonable, because in ANOVA we have a formal test. In R square is just a kind of rule of thumb. So I'll come back to that very soon. So now we are trying to get the ANOVA, and here we go. So this is the analysis of variance here, and you see that the p-value for regression is 0.000. We say that if it is less than 0.05, in general, if it is less than 0.05, we say that the model is acceptable. When this time it's very, very small, just 0.000. That means it's very, very small. That means our chance of accepting the null hypothesis is very low. The null hypothesis is that the model is unimportant, so that we are not believing in. So the model is highly significant because it has a very low p-value, 0.000. F value is 47.48, which is quite big. And this is a formal test. So, of course, R square was 0.862, which is high, of course, but you cannot test that because it's just a rule of thumb. This time we can say p-value is very small. That means we should accept this model. So this is the case that we can say that the fertilizer has significant impact on the production of rice. And that's it. So I think I have just finished on time, probably 5 minutes before my schedule. Thank you, everyone, for your patience hearing. I know that the talk was long, but you are here for a long time, probably for 1.5 hours. So I thank you. And if you have any quick questions or comments, I think probably.
Okay, thank you, sir. That was a fantastic presentation. Actually, we with us, with you. So that was a fantastic session. And data science is a big deal all over the world. Essentially, one of them. So, sir already declared we get sometimes for question answer session. So before that, I want to request to say something about the session to Hindul Bhai from Canada, the director of Associate. Could you say something, Hindul Bhai? And then we'll go to the open question.
Thank you. Thank you, Alamgir and Lincoln. Thank you. It is actually the very good sessions and presentations for those who are actually working in the ground in the data management, data analytics, and support to the management to take the decision making. So these are the very theoretical discussions actually that today discussed, and I hope enlightening by this actually this theory and the good examples who are actually working in our fields. So I appreciate these session arrangements, alumni and our organization, the circle, to arrange this, and hopefully next few next times we may organize such types of some good knowledge sessions about the quality assurance people, those are actually working in the development field. Thank you.
Thank you so much, Hindul Bhai. Actually, Digital Learning Hub is a learning wing of Circle from 2023. So now, open discussion session. There will have a lot of question or feedback on the session, but we'll finish by 20 to 30 minutes, couple of times. Please raise your hand one by one. Those who will not get chance, please write down your opinion, feedback, question, or suggestion in our WhatsApp group or mail to one to one. I will take care your suggestion or by WhatsApp group or other communication channel. So open is floor is open for all. So you can question on by one. Any question to know about the statistics or data science to our respected sir? He's a very knowledgeable sir all over the world. There are some books here written by Dr. Rahmatul Iman. So if you can question rightly, if you can answer the proper way. So you can ask question. Okay.
Alongir, can I actually ask something?
Yes, yes, sure.
Okay, thanks. Actually, the in our ground, we are actually the managing the different projects and data. So most of the case, we actually the collecting our data in the convenient sampling, not actually the addressing the probabilistic model due to the actually the ground realities and also the cost of projects. And sometimes we may actually the collecting data referentials or snowball the way. So those are mainly the non-probabilistic way. So my question is that in our ground, we may collecting the data non-probabilistic way, and then actually the management or seniors or some consultants actually that doing the estimations as like the probabilistic model wise. So how these things actually the valid or non-valid? These are the dilemma. So I am interesting to know about this concern. Is it actually the right or wrong or what actually the stand in aspect of the theories and statistics point of view? Thank you.
Yeah.
Okay, so let me answer this question. It's a very nice question and very valid question as well. So, of course, we have several ways of doing it. So, say for example, network sampling, and not only the case. There are lots of other kind of situations where the results that we get from data are biased. Say, for example, when you are catching fish for a service, even if you are trying to do it randomly, always, if the small fishes they slide through the net, so you cannot catch them, right? You're only catching the big fishes, right? So it can happen in many kind of situations. So even if you try to do it random way, it's not possible. Say, for example, if you try to get information from the drug users, you cannot do it randomly, right? Because you have to get the snowball kind of stuff, or you have to get the networking first. So, and if you do that in that way, and say, for example, when you do the survey through internet, only your friends, as I probably mentioned that when the convenience sample kind of question I raised, that you are only getting information from people who you do know. So it's not necessarily the representation of the entire population. So now the question is, but those are very convenient as well. And even if I tell people that you do it in a random way, people usually do it in non-random way. So now what we can do that even if we do it in non-random fashion, there are some techniques that we call bias correction. So if we can find or identify that what amount of bias this kind of practicing with the network sampling or say internet survey is occurring, then we can correct that. And if we can correct the bias, after that we will get more reliable kind of estimate. So if you allow me, probably I can give you a different session sometimes exclusively on this bias correction techniques for sampling. That will be very helpful, I think, for many of you, those who are really getting information from the ground reality where random samples are not that easy. So this is one answer to this question. Another one is that just like the data science or machine learning stuff, now we have a kind of sampling that is known as hybrid sampling. So what is a hybrid sampling? The hybrid sampling is a mixture of probability and non-probability sampling. Say, for example, I would like to have 100 samples, right? What I am doing now, I am going to randomly pick 20 observations or 10 observations, and I'm getting the same people and getting their, I'm going to get information from the net or some other kind of way. So after this, getting this 20 information randomly and 20 observation in a convenient way, I'm looking at how much difference we are getting from those two approaches. And I would find a bias correction technique. And then after that, I can just get the 80 remaining observations just through internet. And now I know that how much bias correction I need to make for those 80, because I have 20 observations in my hand, and I know that what I should do for correcting bias for this 20. So based on my knowledge, I can now go for bias correction for the 80 remaining observations. So in a reality, what I'm doing now, I'm collecting 20 observations, 1/5 of the observations, or 10 observations means 1/10 of the observations, randomly 90 or 80% observations in a convenient way. And we can now use this 10 for bias correction for the remaining. So this is called hybrid sampling, which is another kind of approach which is getting popular nowadays. But there are lots of techniques that is available in the literature for bias correction related to convenient samples. So if we can do the bias correction, I'm not saying that it will be as pure as the random sample, but it will reduce the bias part a lot. And after that, the answer or estimate that you get after bias correction will be equally as good as a random sample. So I'm sure that if I get time, sometimes later, probably I can give a talk on these issues. So that will be very helpful and very helpful for people who are doing this kind of research. And most of us are doing this kind of research, right? We have to get our data, and random samples are really difficult to get or achieve. And whether we like it or not, most of the time, the information that we get are somehow like this. So bias correction technique would be very helpful. Does it answer your question, sir?
Yeah. Through these bias corrections, can we actually formulate the hypothesis testing?
Yes, if we can do some, if we can recognize some pattern or some distribution. Say, for example, I can tell you one thing, that there are some pattern. Say, let me give you this. The rare disease that follows a Poisson distribution, all you know that, right? Poisson is the distribution of rare items, rare disease.
Yeah,
when the probability is very small, if the probability is very small and if the sample is, if the population is large, that's a Poisson distribution, right? So we often model, this kind of disease kind of stuff by a Poisson model. Accidents, number of accidents, right? Number of rare disease. So these are kind of stuff that we use in Poisson. So now, say for example, you are trying to, investigate patients. How you get your sample? Will you knock door to door and ask people that whether you have this disease or not, or you will go to a hospital or a clinic to get information from there? Which will be more convenient for you? Getting information from a hospital or a clinic for a disease, right?
Sir, in addition that, you mentioned the Poisson distributions, but our hypothesis, most of the normal distribution. So
not always the case. Sometimes we assume that, but you can always approximate Poisson to normal as well, because in terms of sampling, there is a powerful theorem that we call central limit theorem. So if you subtract the mean and divide by the standard deviation, you can approximately make any distribution approximately close to a normal distribution, right? So even if you begin with a Poisson, you can end up with, because binomial, which is another distribution, you can approximate a Poisson from a binomial. You can approximate a normal from a Poisson as well. So of course, rare disease is Poisson, but you can ultimately use normal in the end. And whenever you see that, what kind of test we use in statistics, we either use normal test, we sometimes use T, we sometimes use Z, chi-square, we sometimes use F. But all these distributions are coming from a normal distribution. How we get a student's T? If the numerator is a normal and the denominator is chi-square. How we get a chi-square? Square of a normal. So if there is no normal, there is no chi-square. If there is no chi-square, there is no T. If there is no chi-square, there is no F, right? So if there is no normal, there is no T, no chi-square, no F. So every test is coming basically from a normal. So normality is always there. But of course, the data that we often deal may not be exactly normal, but we can make it approximately normal by the help of the central limit theorem. So there is a logical justification of using normal, even if the data is not exactly normal. So that is one kind of way out that we can always do this. And the other one is always more accurate, that don't use parametric tests, go for non-parametric tests. There are lots of non-parametric tests which do not assume any distribution regarding your data. And now in the era of big data, you do not know the distribution of the data. The data is huge, right? The data is huge. The data is changing all the time. How do you know that your data is normal? Your data may not be normal at all. So if we use the machine learning approaches based on non-parametric techniques, we can get rid of this problem. We do not really need any normal distribution nowadays if we really deal with the big data. And sometimes with this kind of information, while we definitely know that it's Poisson, when I definitely know it's log normal. Say, for example, the live data. Live data is never normal. Do most of the people die at their middle age? No. We usually die when we are old enough, right? But if it is a normal distribution, then what happens? Your mean, median, mode is at the middle, right? So most of the people will die at their middle age. So this is not normal, right? So your life of battery, when you are buying battery, you are buying light bulb, when it will get fused? At its average age? No. They'll survive there, right? So they will die or it will get fused when it's in the extreme time. Its life gets longer. Usually the electronic products, either it fails early, that's why you have warranty period. If it survives first few months or years, it will go for a long time, right? So that's the kind of pattern we have. And that's exponential distribution we usually use there. So lots of distributions are not normal, but we still use normal based on the central limit theorem, one way. Other way is that forget about this parametric stuff, go for non-parametric, where we don't need any assumption regarding any distribution. We can just use the data, get some local information from there, and we analyze the data in that. So that can be another way of looking.
Okay. Another question? Any other question from Hindul Bhai?
Yeah. Thank you, sir. Yeah. Sir, I actually making the lots of the questions. Sorry. Yeah. So very recently, we actually used in many development projects like the baseline or inline. These actually the data reduction model, like the factor analysis or the factor loading. So, what actually the factor actually the related to the actually the resilience of the disaster, or what are the some factors of the nutrition deficiency or market systems? We collecting the different data. So we actually actually the many report now using the principal component analysis or data reduction model.
Right.
So actually they needed to follow the distribution concepts, or only the variable is the variable and observation and information, and we run direct throttling. So what are the actually the behind the theories or actually the logic?
Okay, so basically, all these kind of techniques that you mentioned, like principal component analysis, factor analysis, those are basically multivariate statistics. And those are coming basically from the assumption that your data is multivariate norm. So the normality is there because whenever we are doing this kind of testing, so say, for example, say I have 100 variables, right? But I have only, say, 50 observations. So I cannot run any regression there, because for a regression model or a design model, the number of observations should be more than the number of parameters, right? So in a disease, you have only 20 patients, but you may need to ask like 100 questions. So how you can estimate your stuff? So that's why instead of variables, we just try to get the factors. So we just try to get like combine several variables to one factor. Say I have 100 variables. I just want to make 5 or 10 major factors which can explain the 100 variables. Now, which variables will constitute one factor? So that's a kind of factor analysis, or the principal component, which can tell you that in which combination you can explain most of the variations. So say, for example, how I can explain 90% variations or 80% variations. That's what we do in principal component, right? Which is a kind of combination of variables together, and they're jointly explaining some kind of thing. So this is basically the dimensionality reduction techniques that is often used with the high dimensional data. Basically, these are all coming from normal distribution. We do not see that, but behind the scene, when we group these variables and try to find the significant factors, those are based on F-test. And as I told you before, that F-test comes from normal distribution. So if there is no normal, there is no F. So at the back of our mind, we do not see those, but at the back of our mind, or when the computer is computing that for you, they are comparing F values with when they're preparing or they're constructing this kind of factors or principal components. So yeah, normal theory is there, but the point is that most of the time when we look at the data itself, or they may not look like normal, of course, but still, if you are in a formal statistical techniques, I think still 90 to 95% statistics are still based on the normality assumption. The reality may be something different, but unless you go from parametric statistics or classical statistics, we are not really going away from normal distribution. It's there. It's there. We may not mention that, but whenever we do that kind of stuff, it's always there. Every time we do a t-test or a chi-square test or an F-test, we don't see that the data is normal. We have a data, we have an hypothesis, we just go and do a test. And hardly we check normality of the data, which is, of course, very important. Nowadays, what we say that, the first thing that you have to do whenever you get a data, you test for normality. We have lots of normality tests like Park-Bera test. We have, normal probability plot. So there are lots of ways that you can do the normality test. If you know that your data is not normal, there are some other ways of estimating parameters under exponential distribution, under log normal, under Poisson. So there are some ways of doing that. And the second one is that if it passes the normality test, then go for outlier checking, because this is another important kind of area, that what's the impact of outlier, how it's affecting our inference, right? Because when we have observations, often we see a few strange observations here and there. So that is another kind of point that should be noted. So there are lots of diagnostic checking that we need to do before doing a formal test, but we hardly do that. And sometimes we can ignore those because normality is such a strong kind of distribution that it can accommodate lots of different things. So people know that if you vary from a normal distribution, you could be in trouble. But still, there is the magical theorem that we say, the center limit theorem, which makes everything normal in the end, if the sample size is large. And since nowadays the data is large, they say you can use normal, because for large data, any distribution will ultimately become a normal distribution.
Okay.
So that people usually do. Yeah.
Thank you. Thank you, sir.
Thank you.
Have any question from southern country or Canada, Australia, another country, and is still not question? We will finish. So, have any question from another country? No. So maybe not. So, sir, I want to know last talk from your side, and we'll finish the session. Please say something, and that we will close the session.
Okay, Alamgir, let me thank you one more time, and I'm very pleased to see, although I didn't get too many questions, but the gentleman who asked very, very good questions, and I think he took questions from some kind of questions which came to everyone's mind. So that's why there are not much questions from other people, because he has covered almost every kind of thing that one researcher may have in his or her mind. So I would like to thank the person who asked so many interesting questions, and that was a very lively discussion. And I'm very honored for giving me the opportunity to present in front of you, and I'll be very happy to come here again and again. It may not be 2 hour or 1.5 hour discussion, even if it is for like 2 or 3 speakers in a session could be fine, for like say half an hour or 1 hour with more specific discussion. Today, you see the content was quite big, and that's what you also told me this morning, that the content is really big. So probably next time we could get more focus to particular kind of topic so that we can have more intense discussion, right? So it may take several times, not today, after 3 months, and then after 6 months we can meet again, because you are continuing this, right? So you have an intention to go for this kind of discussion for a long time. Time to time I can come and join you. And I would thank you because you are organizing such a great thing, and which is beneficial for all kind of people, not only for statistics people, people from every discipline. They are getting benefit from your, this kind of session. And I'm really very, overwhelmed to see that people from so many different countries, they are joining your session and they're attending it. I think that at the last time, 60 or more people were there till the end of my discussion. So that was really fantastic to have so many people with us. So I would like to thank every participants who listened to me for a long time, over almost 2 hours. You are listening to me. So let me thank you all. Let me thank Alamgir for giving me this wonderful opportunity, and I wish you all the best. And I hope that it will continue for a long time, and lots of people will come. And I'll be very happy to join your sessions. Thank you so much.
Thank you, sir. There was near about 90 people here in this session. So actually, we'll be grateful to you for this nice session and nice discussion. Thank you very much, sir. I will communicate with next, if I conduct another topics, I will come and I will invite another session. So good night today. All the participants keep patient. So Allah Hafiz from Bangladesh.
Thank you.